in this lecture, we are going to do a few previous year problems that were asked on dynamics of stationary states. So you're already aware that if at initial time t equal to 0, if my wave function is given by psi x comma 0, then we would like to find what is how is this particular wave function uh, behaves with respect to time, or how does it evolve with respect to time. So we are interested in evolution of psi as a function of time also. Okay. And this we already know that whenever we solve the time independent Schrodinger equation, we get the stationary state solutions, and those stationary state solutions evolve with respect to time via this particular formulation. That is, if my wave function is known at any initial time, that is time t equal to 0, then I know that at any later time, my wave function would evolve in a manner given by this equation. That is, psi as a function of x and t is equal to psi as a function of x at time t equal to 0 times exponential minus iota en t upon h ket. This is how my wave function evolves with respect to time. Okay, so I know that the stationary state solutions which I had obtained from time independent Schrodinger equation, they evolve with respect to time using this particular equation. Okay, so you can see that the stationary state solution only have this particular term as a time dependent term. Okay, so I know that in stationary state solution, I'll simply write stationary states as SS. Only the stationary state solution only accumulate. I should write only accumulate this particular function, or you can say this. Sometimes we know as time evolution operator. Also, we say like time evolution as a function of time. Okay. Otherwise, the particular point, this particular thing is independent of time. It is at time t equal to 0. Okay. And we already know, I had done this thing in greater detail, that h ket turns out to be E. And we really, we come to a point to really understand that all the physical properties, for stationary states, you can say are constant in time. So therefore, we tell them we refer to them as stationary states. So this is something that we have already done so far. So if I really want to know, I also know this particular fact that my wave function is forms a complete set. That is, the wave function can be what you can say. The wave function can be written as linear combination or superposition of the eigenkets that I know. And I know this amplitude Cn is simply obtained using the Fourier trick. So for example, if I'm talking of in general, then Cn can be written as minus infinite to plus infinite phi n star x psi x dx. This is how we can find at any, if I want to really find at time t equal to 0, then I can also write time t equal to 0. So this particular amplitude is simply found using the Fourier trick. I have done all these things in greater detail in the lectures. I'm just revising it for you so that you can really understand the context I'm building right now. Okay, so what happens is that since I can express this particular wave function, I can express this particular wave function, you can say that a stationary state in terms of linear combination of various eigenkets. So what happens is that if I want to write how does my state evolve, so I can simply write psi x is equals to summation n equal to 1 to infinity, Cn, phi n x, and then I can multiply this time dependent term here, exponential minus iota ent upon h cat. This is how I can do. So clearly, it's quite evident that evolution of the wave function, or rather I should say the superposition, is precisely the superposition of the evolution. Okay. So each term multiplied with this time evolution term, and then I sum it up, I will get my wave function at any later time t. Okay, I hope this is clear to you. Okay, and we all know that in most of the instructive way to teach quantum mechanics is to really find uh, uh, eigen energy values and eigenstate for a potential problem. So this is our way of learning quantum mechanics, that what we do is we basically try to find for a given potential energy eigenstates, energy eigenstates, and energy eigenvalues. I mean, this is how it is quite instructive to do quantum mechanics. Okay, so now let us understand this particular thing with respect to a problem also. So I have already stated that as a function of time, my wave function can be written as simply summation Cn, and I think phi n, and then I can write exponential minus iota ent upon h cat. This is how I can write my wave function. And rather, I can use one important thing, that I know that this particular thing is independent of time. I can also write it in this fashion. I can use this particular term. I can put it inside this particular Cn. So I can simply write Cn exponential minus iota ent upon h cat time, a function which is independent of time. So it only depends on x. Okay, this is also I can manipulate my wave function. So I can write it as in this fashion also, that is summation Cn as a function of time times phi nx. This is also how I can manipulate things, manipulate my equation. But why have I written it? Because this particular thing emphasizes the fact, this particular thing emphasizes the fact that the amplitude, that this particular Cn evolves with time, that is the amplitude for a particle to have energy En. This particular amplitude also evolves with time. So, I mean, the same way, I mean, same thing, but said in a different way. Okay. And later on, we are going to see it in the sense of momentum also. How does that, like if I express my wave function in form of momentum, not in terms of x and t, rather from p to t, then we'll see that how does it have a relationship. So basically, in the later lectures, I'm going to show what are the relation of psi expressed in momentum space with respect to initial time. So I'm leaving it for a further discussion, not right now, because my today's task is to solve a few problems, and these are, I mean, there are 3 to 4 problems, and these are very interesting problems that have been asked in the examination time and again. So I hope this particular background you might have got. So let us understand this particular scenario with respect to a particular problem, I would say, rather. And that problem is fairly simple, and the problem is called the bouncing particle problem. So I'm just considering a particle which is a simply bouncing particle. Simply bouncing particle. So just as an example, I'm solving a problem. I have done it in, I think, previous lectures also, but just for to set the context of solving the problems that I'm going to do today, I'm just going to discuss something called a simple bouncing particle. So I really want to see that if I'm given a particle which is bouncing back and forth, and I really want to know that in this particular problem, how the superposition of energy eigenstates evolve with time. Okay. And so therefore, I'm interested in the dynamics of the energy eigenstate. Okay. So let us consider a wave function at time t equal to 0, which corresponds to simply bouncing particle. And why I'm telling it simply bouncing particle, you will come to I mean, I'll come to this when I'll show you this particular graph and the why I have chosen this particular graph. So simply bouncing particle. So I have basically made you understand the problem is that a particle is bouncing back and forth. And now I really want to know that how does the superposition of energy eigenstates evolve with time. So basically I'm taking a infinite deep square well only. So basically particle goes from here to here. So it is trapped inside this potential. The wave function at any initial time t equal to 0 is given by 1 over root over 2 phi 1 x plus phi 2 x. So this is how I have my initial wave function. So the initial wave function is prepared in terms of the eigenkets phi 1 and phi 2. And simply I can write this as simple 1 over root over a. And let's say this is the length of the box is simply a. So 1 over root over a sine pi x over a and plus 1 upon root over a sine 2 pi x upon a. Okay, so wave function of the particle obviously here is 0. So that's something that I really should not, I mean, I have already taught you all these things, so I'm not going to do that. But for the infinite potential, the wave function is simply 0 here. But where the particle is trapped, I mean, where the particle is moving back and forth, here the wave function is given in this form. Okay, so basically what is happening that this particular wave function is the superposition of the ground state and the first excited state. Okay, and if I want to write what would be the wave function at any later time t, I think it's fairly easy to see that it would be simply uh, 1 over root 1 upon root over a sine of pi x upon a exponential minus iota e1 is simply pi square h ket square minus n square pi square h ket square upon twice ma square. Okay, and t upon h ket. So this cancels out and simply t remains here. Okay, so I hope it is clear. And then another factor would be 1 upon root over a sine of 2 pi x upon a exponential minus iota. This would be 4 and then divide by 2. So 4 pi square h ket t upon twice ma square. If you plot this particular graph, I mean, this is something that I'm leaving up to you. You'll find that the graph happens to be this way. The graph happens to be this way. So if I plot this particular thing, that is 1 upon root over a sine pi x upon a plus 1 upon root over a sine 2 pi x upon a, then graph happens to be this way. I mean, how can you plot it? That also I can tell you. It's very simple. That whenever you have to plot a sine theta plus b sine theta, try to make it in one one particular thing. So what you can do is simply divided by root over a square plus b square here also, and divided by root over a square plus b square, and then try to write it in some form that is one trigonometric form, that is either write it in cos or either write it in sine. After having written this, you can do this, or you can simply write here. It's very simple to see that it's 1 over root over a. You can take common sine a into sine a plus sine b formula. If you can take common out, and then you will find that this will be the graph. So I'm just plotting the graph right now just to show you something. So I'm just plotting the graph. Graph is this way. Now it is clearly visible that if I take psi mod whole square, so it will be what? It will be like this. So it's quite evident that it would be like some smoothness would be here. So it is quite evident that the probability amplitude of the particle lying on the left side of the well okay, so on the left side of the well, you can see, so for example, it is like greater than a/2. So somewhere a/2 would be here. And I know that probability of finding the particle, or I should not use the term that, probability of, you can say probability amplitude of finding the particle on the left side of the box of left side is greater than probability of finding the particle on the right side. Okay, this is quite evident from the graph. So, I mean, I'm just giving you an extra information here. Okay, but the time evolution happens to be this. And if I really want to find what would be psi x comma t mod whole square, which dictates my probability amplitude. So this probability amplitude turns out to be, I'm just showing it to you, it will be 1 upon a sine square pi x upon a plus 1 upon a sine square 2 pi x upon a. And then there would be some term which is like mixed term. So this will be 2 sine pi x upon a into sine 2 pi x upon a times. There would be some factor. I mean, that I'm not solving. I hope I'm leaving it to you to solve this particular thing. It will come out as cos of 3 pi square h ket t upon twice ma square. I have done this particular problem initially also, but just as a manner of revising a few concepts, I'm doing it. So again, I'm coming back to the problem. The simple bouncing particle, that is particle which is trapped in an infinite potential well. The wave function initially is prepared in the state phi1 and phi2. And at any later time t, I can write my wave function in this fashion. I know from the graph that the probability of finding the particle on the left side of the box is greater than the probability of finding the particle on the right side of the box. And psi mod whole square is simply 1 over a sine square pi x upon a plus sine square 2 pi x upon a. And then there is an additional term. And this additional term, it depends upon time. Okay. So this particular term is quite interesting because the interference of these two states is being encapsulated from here. So basically, what should I say? That this particular term I can refer to as an interference term. And this interference term is dependent upon time. Okay, so all the time dependence is encapsulated in this interference term. So this is dependent on time. So this particular interference term contains all the time dependence of this particular probability amplitude. Okay, the initial two terms doesn't contain, I mean, you can clearly see that this particular term doesn't contain a time dependence. This particular term doesn't contain the time dependence. All the time dependence of the probability density is encapsulated in the last term, which I'm referring to as an interference term. I mean, it's not a scientific jargon, but okay, that's kind of way of, that's kind of way I've used it. This is an interference term, okay? So what happens is that overall, this particular spatial profile, that is space dependent profile, oscillates with this particular, oscillates, I mean, you can say sinusoidally. Okay, so sinusoidally, this oscillates. And so sorry about it. So this particular sinusoidal term, this particular spatial term means what? That depends on time, oscillates with this particular, oscillates due to this particular term, oscillates due to this interference term, which I'm referring. Okay, so okay, this oscillates due to this interference term. Okay, and I had done it before also. What would be the time period of oscillation? It will be equals to h ket 2 pi h ket upon E2 minus E1. And that is equals to what? It is simply 4ma square upon 3 pi h ket. I would urge you to really go back and see this particular question, or you can say this particular topic I've already covered. So I'm just referring it right now, that this particular term, okay, this particular term, which is a spatial term, is multiplied with this oscillating term. So basically, this particular term oscillates with a particular frequency, which is 4 ma square upon 3 pi h cat. And this particular term gives a time dependence to the probability amplitude. And you can clearly see that at time t equal to 0, that at initial time, I told you that the probability of finding the particle on the left half of the box, is what you can say. Okay, is on the left half of the box is more than the probability of finding the particle on the right half of the box. Okay, and this is quite evident from the graph. You can say a by 2 would lie somewhere here, and you can clearly see that probability of finding the particle on the left half of the box would be more than the probability of the particle lying on the right half of the box. And now what happens is, let's say I take time t equal to t by 8. What will happen? I have to place t by 8 here, and I can see clearly that my probability now shifts with respect to time. Okay, so probability amplitude now shifts towards the left half of the box. And slowly, we see that now at time t equal to pi by 4, the probabilities of finding the particle will be almost equal on both sides. And this is how it is going to oscillate. So this represents your oscillating, what you can say, probability density. Okay, so this particular problem is an important problem to really demonstrate that within each period, how this particular probability density evolves, and how the possibility of finding the particle from one half of the box and other half of the box evolves. And when you can also really understand that, really see here the particle evolved, this particular area increased. So basically on the right of the box, now the probability of finding the particle slightly increased, and then almost equal here. And now here the probability of finding the particle on the right half of the box increases. So basically we can say that particle roughly bounces from back and forth. Particle roughly bounces back and forth. Okay, in terms of probability only. Okay, back and forth. It's not classically, but in terms of with certain probability. Okay, with certain probability attached, particle roughly moves back and forth. And this particular, all those things generates to this particular interference term. Okay, so we have to really understand that whenever, if you had a single particular thing, like if the wave function initially was only prepared in phi1 or phi2, only phi1 or only phi2, then this particular interference term would have not existed. So whenever these superpositions of more than 2 energy eigenstates come, then it really gives birth to some intricate dynamics. And this is what I really wanted to display. And you can really see from one of the, I think I'll just try to show you if you really want to see. Just give me a minute. Okay, so if you really want to see, I can also show you using an image, and then you will be able to really appreciate it. See, here it is. So you can really see that the probability density is now moving with respect to time. Okay, and on the right hand side, you can see it with respect to x, that is psi mod whole square, which is the probability density. So with respect to time, it is evolving. And also there is a image that is being shown where the real part and imaginary parts are also shown to you. So I hope this particular image gives you certain insight. And that's why I focus on the problems that were asked in the examination, which was, what you can say, which actually utilize this concept of dynamics of the, what you can say, dynamics of the energy eigenstates. Okay, so here the question is given to you that the eigenstates corresponding to the eigenvalues E1 and E2 of a time-independent Hamiltonian R, ket1 and ket2, respectively. If at time t equal to 0, if at time t equal to 0, the system is in state psi t equal to 0, which is sine theta, and then ket1 plus cos theta ket2, then we want to find what would be the value of this particular expression at later time t equals to t. Okay, so again, this is easy problem. It's not that difficult. So I know that initially my state at time t equal to 0 is given to be sine theta get 1 plus cos theta get 2. And I know that this square plus this square is 1, so that's not a trouble. I want to know what would be my wave function at any later time t. It would be simply sine theta get 1 exponential minus iota even t upon h get plus cos theta get 2 exponential minus iota e to t upon h get. Okay, I know this already. Now, if I want to find, so this is how my psi t would be. So if I want to write in ket notation, it is simply sine theta ket 1 exponential minus iota even t upon h ket plus cos theta ket 2 exponential minus iota e to t upon h ket. Okay, so this is how my wave function at any later time t. And if I want to find what would be psi and psi, so basically it implies the norm of this particular wave function psi t, which would be simply, I would write it here. It would be sine square theta. Okay, then cos square theta, and that, and again, one interference term should come, and that we'll write it here. So interference term, so I'm just writing it here once, sine theta, this, and then exponential iota even t upon h ket plus cos theta ra 2 exponential iota e to t upon h ket times this entire thing sine theta. Okay, so basically these two terms I have written, so I'm not going to write it. Okay, plus cos theta exponential minus iota e to t upon h ket. Okay, I'm doing it for the mixed terms. Okay, these two terms I've already done. So this particular product I've already written it here, and this particular product I have already written it here. So now I have to write the mixed term. So the mixed term I'm going to identify from here. Okay, so let me just identify and then I'll write it here. So what would be that mixed term? So mixed term would be simply psi is equals to sine square theta plus cos square theta is simply 1 plus, okay, and now I'm finding the mixed term. So mixed term would be equals to what? 2 sine theta cos theta exponential of iota even t, even minus e2 t upon h ket plus 2, plus not 2, plus cos theta sine theta exponential iota e2 minus e1 t upon h ket, and then this entire thing multiplied by ket 1 ket 2. Okay, okay, and this will give you 1 plus if I take sine theta cos theta, I mean common out, then I'm getting this particular thing exponential iota theta plus exponential minus iota theta. It is 2 times cos theta, so 2 times real part of what you can say exponential minus iota e1 minus e2 t upon h ket and times ket 1 and ket 2. Okay, and then there would be some sine theta cos theta also. Sine theta cos theta. I know that these ket 1 and ket 2 are orthonormalized. So I know this particular thing would be simply 0 So this goes to 0. It implies what? It implies that this probability amplitude psi psi is simply 1. So I hope this solves your question. Okay, so here it was given to you, and this is what I have written. I hope it is clear. So I think 1 should be an answer for this particular problem. So this was asked in, I think, CSR net only. So this particular question you should be able to do now. Okay, so if you have any trouble, kindly let me know. I mean, I was just trying to find a mixed term here. Okay, so for that I wrote the entire expression. I know you will be able to make sense out of it. So okay, I was just finding this mixed term, because this term, that is sine theta ket 1 exponential iota even t upon h ket, and sine theta ket, sorry, this is bra 1 and this is ket 1 exponential minus iota even t upon h ket. So this cancels out. Ket 1, sorry, 1, this particular thing would become 1. This particular thing would become 1. So sine square theta plus cos square theta is fine. The remaining thing would be simply sine theta ket 1, and here you, sorry, bra 1, and you have a ket 2 here. So multiplies sine theta cos theta, you'll get exponential iota even minus e2 t upon h ket, and then plus cos theta sine theta exponential iota. This is e2 minus even. You can also write it as minus iota even minus e2 t upon h ket. So basically, you already know that e raised to power iota theta plus e raised to power minus iota theta is nothing, but it is 2 times cos theta, which is nothing, 2 times real of e power minus iota theta if you want to write, or you can write e raised to power even iota theta, whichever thing suits you. But the point is that at any later time t also, this probability amplitude remains the same, which is 1. At any later time t equals to, at any later time t, this probability amplitude remains equal to b equals to 1 only, because this particular thing goes to 0. I hope it is clear so far. Now let us move to another question. And the question that was given to us was this. This has been a favorite question of NET and JEST exam. So it has been asked, I think, twice or thrice in NET also and JEST also. So let us do this particular problem. I think this has been asked in JEST also and NET also. I mean, this is easy question. That's not a worry. See, if psi1 and psi2 denote the normalized eigenstates of a particle with energy eigenvalues E1 and E2 respectively, with E2 greater than E1, at time t equal to 0, the particle is prepared in state. So at time t equal to 0, we know that my particle is in state what? 1 upon root 2 psi1 plus 1 upon root 2 psi2. Okay, I know, I mean, this particular thing I already know. We've done it previously. The shortest time t at which psi t will be orthogonal. Okay, so orthogonal means what? It means that if I want to find orthogonality, it implies psi t. If I want to find this should be equals to what? This should be equal to 0. So this would be my condition for orthogonality. So at any later time t, that is capital T, my wave function would be what? My wave function would be simply 1 upon root 2 psi1 exponential minus iota E1 capital T upon h ket plus, or I should write first small t and then I will write at time t equals to capital T. That would be more, I mean, that would be better. So 1 upon root 2 psi2 exponential minus iota e2t upon h ket. Okay, now let us do the problem. So I want to find the shortest time in which psi t, psi 0 becomes 0, which implies what? It implies root 2 phi 1 star, psi 1 star exponential iota e1 t upon h ket plus 1 upon root 2 psi 2 star exponential iota e2t upon hket times 1 upon root 2 psi 1 plus 1 upon root 2 psi 2. This particular fellow becomes 0. And I know that psi 1 star psi 2 would be 0 because these are uh, orthonormal states. So what remains to us is simply 1 upon 2 psi 1 star psi 1 is simply, I would write it here so that I would simply get exponential iota e1t upon hket plus exponential iota e2t upon hket equals to 0 at time t equals to capital T. So I know that this particular thing should be equal to 0 at time t equals to t. I hope it is clear so far. So what do I get from here? I get something like this. Now see, it has been given to me that E2 is greater than E1. So E2 is greater than E1. So what I'll do, I'll simply take E1 common out. I will simply take E1 common out. Okay, so I'll simply take E1 common out. Here it is, sorry. I'll take E1 common out. Exponential iota E1, sorry. Exponential iota E1 t upon hket common out. And I will simply get what? Simply get 1 plus exponential iota E2 minus E1 time at time t equals to t. So I'll write capital T, or I'll see, I'll write now small t only upon hket. This should be 0. This particular factor cannot be 0. This is an oscillating term. And so the solutions can be found from here. It is exponential iota E2 minus E1 t upon hket must be equal to minus of 1. And I know that from complex, I know that exponential iota 2n plus 1 pi is equals to minus 1, because I know that exponential iota theta is what? Cos theta plus iota sine theta. And I want to have a real minus 1. So I will have to place odd multiples of pi. This will be minus 1. Always remember, cos n pi is always equals to minus 1 raised to power n. So at all these multiples of pi, sine becomes 0. So cos remains minus 1 raised to power n. So if it is odd, then it is minus 1. So I've written e power iota 2n plus 1 pi. T upon hk. So clearly I know what would be my time. My time would be equals to 2n plus 1 pi hk upon E2 minus E1. And they've asked for the smallest time. So smallest time would correspond to n equals to 0. So the smallest time interval in which my states becomes orthogonal is pi hk upon E2 minus E1. I hope this solves your problem. This is your problem from NET exam. Now let us do a problem from your, I think TIFR. If this particular problem was asked in TIFR exam. So I'm going to do this particular problem, and this would be the last problem in this particular session. I hope I have not disappointed you. If you really feel that there is some doubt, kindly let me know in the comment section, because at times I go a little bit faster. Just give me a minute. Okay, I hope the thing is visible to you. If it's not, let me make it slightly bigger. So this was asked in TIFR exam, this particular question. So question is fairly simple again. It says that the wave function of a quantum mechanical system is described by Hamiltonian, which is written as linear combination of phi 1 and phi 2, which are the eigenfunctions of hk with eigenvalues E1 and E2. Okay, okay. So it is known to us that that okay, it is known to us. Sorry. It is known to us that phi 1 and phi 2 are eigenfunctions of hk with energy eigenvalues E1 and E2. And now they're asking us that initially the system is prepared in this particular state, which is at time t equal to 0, we are given that the wave function initial is 4 by 5 phi 1 plus 3 by 5 phi 2. Now we want to know that at any later time t, if it is left to evolve with time, at any later time t, which is given by 1 upon 2 h E1 minus E2, what will be the wave function accurate within a phase? So at any later time t equals to small t, let me write, it will be 4 upon 5 phi 1 and then exponential of minus iota E1 t upon h ket and then plus 3 upon 5 phi 2 exponential of minus iota E2 t upon h ket. Okay, and it is given E1 minus E2, it implies E1 would be greater. So I would simply take, so let me do it. Okay, so wave function at any later time t, which is given to us, would be. So this is not even finding, this is simply finding at later time t equal to t. So I will simply place this thing, that is psi at any time t. What should I take common of? I will simply take exponential of minus iota E1 t upon h get common out. So what I'll get, I'll simply get 4 upon 5 phi 1 and plus 3 upon 5 phi 2 exponential iota E1 minus E2 t upon h get. And now it is given to me that the wave function at any later time t. So at any later time t, which is simply h upon 2 E1 minus E2, what would be my wave function? It would be equals to, I mean, this particular phase factor would remain. So this is what they're saying, that barring this phase factor, what would be my wave function? So within a phase, we want to write this is the phase, and within this phase, this is the wave function. So at any later time t, my wave function would be associated with the phase factor, which I should not be bothering at all. Okay, so leave this particular phase factor. What is the wave function within that phase factor? This is what has been asked in TFR exam. So this is 4 by 5 phi 1 and then plus 3 by 5 phi 2. And then you have this exponential iota E1 minus E2 t upon h ket. Place this particular fellow. So exponential iota E1 minus E2. What is h ket? H ket is simply h upon 2 pi. So 2 pi comes here. And what is t? T is simply 1 upon 2 h upon E1 minus E2. So this cancels out, h cancels out, and you are only remained with the exponential iota pi. So the wave function within a phase factor is nothing but within a phase factor is nothing but 4 upon 5 phi 1 plus 3 upon 5 phi 2 into exponential iota pi. And what is exponential iota pi? It is minus 1. So answer should be 4 upon 5 phi 1 minus 3 upon 5 phi 2. I hope this solves your problem. This is a problem which was asked in TFR, I think, very initial years of TFR when TFR started this paper. I think this is TFR 2010. Okay, so I hope this, like, you might have got benefited by this lecture. Kindly let me know if you have any doubts and difficulties in the comment section. Till then, take care. Bye-bye.